What specific problem does Tokenformer aim to solve in the context of existing transformer architectures, and what is the significance of this problem in the field of deep learning?
Tokenformer aims to address the scalability limitations of existing transformer architectures, particularly the inefficiencies associated with token parameter interactions that rely on prescribed linear projections. This design constraint necessitates retraining the entire model from scratch when increasing model size, leading to excessive resource consumption and impracticality in large-scale applications. By introducing a fully attention-driven architecture that treats model parameters as tokens, Tokenformer enhances the flexibility of token parameter interactions, allowing for incremental scaling and the effective reuse of pre-trained models. The significance of this problem in deep learning lies in the growing demand for larger models that can efficiently process multimodal data without incurring prohibitive training costs, thereby facilitating advancements in various domains such as natural language processing and computer vision. Ultimately, Tokenformer's approach not only reduces training burdens, but also maintains competitive performance, making it a crucial development in the evolution of foundation models.
Can you break down the workings of the Tokenformer architecture step by step, illustrating how it reformulates token parameter interactions using the attention mechanism?
The Tokenformer architecture reformulates token parameter interactions through a novel token parameter attention layer, which utilizes the attention mechanism to unify computations. Initially, it introduces two sets of learnable parameter tokens. One set serves as keys, k_p, and the other as values, v_p, allowing input tokens to interact dynamically with these parameter tokens. The output from the potential layer is computed using a modified softmax operation to stabilize gradients, enhancing performance compared to traditional methods. This design decouples the number of parameter tokens from the input and output channel dimensions, enabling flexible scaling by appending new key-value pairs without altering existing model parameters. Consequently, this architecture allows for efficient reuse of pre-trained models, facilitating incremental scaling while maintaining competitive performance across various tasks.
Provide a simple and illustrative example to demonstrate the inner workings of the potential layer in Tokenformer, explaining how input tokens and model parameters interact during computations.
The potential layer in Tokenformer operates by treating model parameters as learnable tokens, which allows for flexible interactions with input tokens. For instance, consider a scenario where we have input tokens represented as I in math bbr_t times d_1, and a set of n learnable parameter tokens, k_p in math bbr_n times d_1 for keys and v_p in math bbr_n times d_2 for values. During computation, the input tokens serve as queries, and the model parameters, the key-value pairs, are used to compute attention scores through a cross-attention mechanism. Specifically, the output is derived by calculating the dot product between the input tokens and the keys, followed by applying a modified softmax operation to obtain attention scores, which are then used to weight the values. This design allows the potential layer to dynamically adjust the number of parameters involved in the computation, enabling efficient scaling and the reuse of pre-trained models without disrupting the learned distributions.
What are the primary advantages of using Tokenformer over traditional transformer architectures, particularly in terms of scalability and training efficiency?
The primary advantages of using Tokenformer over traditional transformer architectures lie in its enhanced scalability and training efficiency. Tokenformer employs a novel token parameter attention layer that allows for the flexible handling of model parameters as tokens, enabling incremental scaling without the need to retrain the entire model from scratch. This design significantly reduces training costs, as demonstrated by the ability to scale from 124M to 1.4B parameters while achieving performance comparable to training from scratch, but with only 1/10 of the computational budget. Additionally, Tokenformer's architecture preserves the integrity of pre-trained models, allowing for seamless integration of new parameters without disrupting the existing output distribution, which promotes faster convergence during training. Overall, these features make Tokenformer a more resource-efficient and adaptable solution for developing large-scale foundation models.
How did the authors validate the effectiveness of Tokenformer, and what datasets or benchmarks were utilized in their experiments?
The authors validated the effectiveness of Tokenformer through a series of experiments that assessed its performance on both language and vision tasks. They utilized the Open Web Text corpus for training, which is a widely recognized dataset approximating OpenAI's WebText dataset, comprising textual data from over 8 million Reddit-shared documents. For benchmarking, they compared Tokenformer against existing transformer-based models using standard autoregressive language modeling tasks, evaluating metrics such as perplexity and zero-shot performance on the PILE dataset. Additionally, they conducted visual modeling experiments, comparing Tokenformer to the Vision Transformer, VIT, on the ImageNet 1K dataset, demonstrating that Tokenformer achieved competitive performance across these benchmarks. The results indicated that Tokenformer not only matched the performance of standard transformers, but also did so with significantly reduced training costs.
What were some specific results achieved by Tokenformer in terms of performance metrics such as perplexity, and how do these compare to the performance of other transformer models like GPT-2?
Tokenformer demonstrated a test perplexity of 11.77 at the 1.4b parameter level, which is comparable to the perplexity of 11.63 achieved by a transformer model of the same size trained from scratch. Notably, Tokenformer required only 1/10 of the training costs associated with the scratch-trained transformer, highlighting its efficiency in scaling. Additionally, when both models were subjected to an equivalent computational budget of 30B tokens, Tokenformer achieved a lower perplexity of 11.77 compared to the transformer's 13.34. This indicates that Tokenformer not only matches the performance of established models like GPT-2, but does so with significantly reduced resource consumption, validating its effectiveness as a scalable architecture. Overall, these results underscore Tokenformer's competitive performance in language modeling tasks relative to traditional transformer models.